a 2003 B6. So a diver descends from a salvage ship to the ocean floor at a depth of 35 meters below the surface. The density of ocean water is 1.025 times 10 to the third kilograms per meter cubed. Okay, so first we have to calculate the gauge pressure on the diver on the ocean floor. So we know that the gauge pressure there equals height times density times gravity. So our gauge pressure, our height is 35 meters. Our density is 1.025 times 10 to the third kilograms per meter cubed. And our gravity is 9.8 meters per second squared. Multiply that all out, and we get our pressure of gravity to be 351,575 kilograms per meter per second. Kilograms per meter per second squared, or newtons per meter squared. So that will bring our final gauge pressure to be 3.5 times 10 to the fifth newtons per meter squared, or more commonly pascals. Okay, so part B, calculate the absolute pressure on the diver on the ocean floor. So we know that absolute pressure is equal to our gauge pressure plus our pressure of our atmosphere. So we know that our gauge pressure, we calculated in part A, is 351,575 newtons per meter squared. And just from a simple 1 atm to Pascal conversion, which is also newtons per meter squared, we get 101,300 newtons per meter squared. Add the two up, and your absolute pressure is 452,875 newtons per meter squared, which can then also be simplified to 4.5 times 10 to the fifth pascals. Okay, so now we have some new information. We now know that the diver finds a rectangular aluminum plate having dimensions 1 by 2 by 0.03 meters. A hoisting cable is lowered from the ship, and the diver connects it to the plate. The density of aluminum is 2.7 times 10 cubed kilograms per meter cubed. Ignore the effects of viscosity. Okay. Part C, calculate the tension in the cable if it lifts the plate upward at a slow constant velocity. So, from a simple force diagram, we can find out that our buoyancy force plus the force of our cable is equal to our force of gravity, right here on the right side of the page. So, we've got to manipulate the formula a little bit and find that the force of buoyancy equals the mass of water displaced times the gravity plus the force of the cable equals the mass of the object times gravity. Take it further, change mass into the volume of water displaced times the density of water times gravity plus the force of our cable equals the volume of our object times the density of our object times gravity. and it's about to get messy, so I apologize. The volume is equal to length times width times height, which is 1 times 2 times 0.03. The density is 1.025 times 10 cubed kilograms per meter cubed. And the gravity is 9.8 meters per second squared. I didn't include units because it took up too much space. Plus the force of the cable equals the volume of the object, which is the same as the volume displaced, so 1 times 2 times 0.03, times the density of the object, which is 1.025 times 10 to the third kilograms per meter cubed, and times gravity, which is 9.8 newtons per meter squared. So delete all that, and when you multiply all that out, you get 602.7 newtons plus the force of the cable equals 1587.6 newtons. So just subtract 602.7 and you get the force of the cable equal to 984.9 newtons. Okay, for the last part, D, will the tension in the hoisting cable increase, decrease, or remain the same if the plate accelerates upward? So, if the plate accelerates upward, then we know that our force diagram has changed. And if it's accelerating upward, we know that the upward forces are greater than the downward forces. So, our force of buoyancy can't change, and neither can our force of gravity. So, our force of our cable must increase. Okay, since the force of our cable is increasing, and force and tension are directly related, then since our force is increasing, then our tension will also increase.